Continuing another video in this series where I left off without the echo, hopefully. Both mics open. Can't do that. Anyway, so hopefully everything will work and such.
Like that, whereby we just will assume naively that Ohm's law holds. In other words, we will always assume that the values for the resistances that we give you will not change. So we will assume that the heat that is produced will not play any important role. So we will just use Ohm's law for now, and if you can't use...
Yeah, so you are sort of stuck with it, and you can never really anticipate all this stuff. I mean, I remember doing the circuit boards, there was always problems with some leakage from one circuit would be making too much noise or doing something, or vibration or this or that, or heat. And you'd have to move parts to different locations to try to create a lack of unintended influences.
It will be very specific about that. So suppose I have here, between point A and point B, suppose I have two resistors, R1 and R2. And suppose I apply a potential difference between A and B, that this be plus and this be minus, and the potential difference is V. And you know V, this is known, I give you V, I give you this resistance, and I give you that one. So I could ask you now, what is the current that is going to flow? I could also ask you then, what is the potential difference over this resistor alone, which I will call V1, and what is the potential difference over the second resistor, which I call V2? Very straightforward question. Well, you apply now Ohm's law, and so between A and B there are two resistors in series. So the current has to go through both. And so the potential difference V in Ohm's law is now the total current times R1 plus R2.
So this is sort of, it probably should be taught as a concept, series and parallel. And just point out that for some components, putting them in parallel will half their effect, and in other components it'll double in effect, and it just kind of depends on what factor you're increasing, and but okay.
Suppose these two resistors were the same, they had the same length, same cross-sectional area. If you put two in series, you have twice the length. Well, so twice the length, remember, resistance is linearly proportional with the length of a wire. And so you add them up. So now you know R1 and you know R2, you know V, so you already know the current. Very simple. You can also apply Ohm's law.
I think the way he said that was kind of useless. The length of the wire, obviously resistors don't usually, well, big ones have wires, but most resistors are composites that just have dirt in them, impurities that make the flow of impede the flow of the electricity.
As long as it holds
Rocks.
for this resistor alone. So then you get that V1 equals I times R1. So now you have the voltage over this resistor. And of course V2 must be the current I times R2. And so you have solved your problem. All the questions that I asked you, you have the answers to. We could now have a slightly different problem, whereby point A is here. But now we have a resistor here, which is R1. And we have here R2. This is point B. And this is R2. And the potential difference is V, that is again given. And now I could ask you, what now is the current that will flow here? And then I can also ask you, what is the current that would go through resistor 1, and what is the current that would go through resistor 2? And I would allow you to use Ohm's law. So now you say, aha, the potential difference from A to B going this route, that potential difference is V, that's a given. So V must now be I1 times R1, that's Ohm's law for this upper branch. But of course you can also go the lower branch, so the same V is also I2 times R2. But whatever current comes in...
Right, so they just add the two. It's not the same V. Well, I mean, that's just kind of whatever. I mean, obviously you're going to add those two hunks of voltage. So, but whatever. well have them in this case, right? But anyway, it should have been the current equals v squared over r would have been a better formula.
And here must split up between these two. Think of it as water. The number of charges that flow into this juncture continue on. And so I, the total current, is I1 plus I2. And so now you see you have all the ingredients that you need to solve for the current I, for the current I1, and for the current I2. And you can turn this into an industry. You can make extremely complicated networks of resistors. And if you're in course 6, you should love it. I don't like it at all. So you don't have to worry about it. You're not going to get very complicated resistor networks from me. But in course 6, you're going to see a lot of them. They're going to throw them, stuff them down your throat. The conductivity of a substance goes up if I can increase the number of charge carriers. If we have dry air and it is cold,
Charge carriers, I like that. But that's really just pressure carriers, which are always going to be atoms, okay? And the thing that's going to, the electron isn't really a carrier. Well, I guess it is in a way, but it's like a half a carrier. The real carrier is the atoms.
then the resistivity of cold, dry air at 1 atmosphere, so rho for air, cold, dry, 1 atmosphere. Cold means temperature that we have outside.
Yes, it really is important in a sense, just because I've been trying to do some charge experiments, duplicating some of this stuff, and it's too humid in here. Hard to get anything to hold a charge.
It's about 4 times 10 to the 13. That is the resistivity of air. It is about what it is in this room, maybe a little lower because the temperature is a little higher. If I heat it up, the air, then the conductivity will go up. Resistivity will go down. Because now I create oxygen and nitrogen ions by heating up the air. Remember when we had this lightning, the step leader came down, and we created a channel full of ions and electrons at a very low resistivity, a very high conductivity. And so,
from the bumping of the atoms, you ionize them. So yes, the warmer the air, the more ions you have, but the more banging there's been going on. And the ions have as their implication an electron that may be bouncing around also.
what I want to demonstrate to you that when I create ions in this room, that I can actually make the conductivity of air go up tremendously. Not only will the electrons move, but also the ions now will start to move. And the way I'm going to do that is I'm going to put charge on the electroscope. Oh, that is not so good. No harm done. I'm going to put charge on the electroscope, and you will see that the conductivity of air is so poor that it will stay there for hours. And then what I will do, I will create ions in the vicinity of the electroscope. Let's first put some charge on the electroscope. I have here a glass rod, and I'll put some charge on it. Okay, that's a lot of charge. And the air is quite dry.
Yeah, I've had no luck doing that. I didn't get charged to stick to anything. Anyway, continuing.
Conductivity is very, very small, and so the charge cannot go off through the air to the surroundings, to the earth. But now we're going to create ions there by heating it up, and I decided to do that with a candle, because a candle is very romantic, as we all know. So here I have this candle. Look how well the charge is holding it. And here's my candle.
Unfortunately, a candle also pollutes, creates a lot of other kinds of chemistry. So I don't know if it's a perfect thing for creating ions, because it also creates a lot of other compounds, but whatever. maybe even some moisture.
And I will bring the candle, or maybe 20 centimeters from the electroscope. Look at it, look at it, it's already going. It's about 15 centimeters away. I'll take my candle away, and it stops again. So it's all due to the fact that I'm ionizing the air there, creating free electrons as well as ions, and they both participate now in the current, and the charge can flow away from the electroscope to the earth because the conductivity now is so much higher. I stop again, and it stops. You see in front of your eyes how important the temperature is, in this case, the presence of the ions in the air. If I have clean distilled water, I mean clean water. I don't mean the stuff that you get.
Okay, so yeah, with the obvious water examples of salt. But yeah, it's good to know. Heat. It would have been, like I said, if we did with a light bulb, it would have been more interesting just to see that it was just the heat. Or a heat source that's covered, so there's no photons involved to confuse anything.
Cambridge. Let alone that I mean the stuff that is in the Charles River. I mean clean water that has a pH of 7. That means 1 out of 10 to the 7 of the water molecules is ionized, H plus and OH minus. The conductivity, by the way, is not the result of the free electrons, but is really the result of these H plus and OH minus ions. It's one of the cases whereby not the electrons are the major responsibility for current.
There you go. So that's really important, because he's basically saying right there that there's atoms that are going to share their ionization, essentially. And it's the sharing of the ionization, the transporting of it from atom to atom, that's really the cause of the migration of the force. Not necessary to have electrons freely fly somewhere and hit something and impose the pressure. But like I said, I think it's reasonable to say that both things have an effect. But it's like the idea of when they supercool something, they're basically removing all this extra stuff, the extra electrons, anything not well bound, and the conductor is more efficient because it doesn't have to shoot anything, it just has to barely vibrate to transfer ionization from one atom to another.
If I add 3% of salt in terms of weight, then all that salt will ionize, so you get sodium plus and Cl minus ions. You increase the number of ions by an enormous factor. And so the conductivity will soar up by a factor of 300,000 or up to 1,000,000, because you increase the ions by that amount.
So again, I've been using the word ions, and he's kind of demonstrating right here that you can, obviously, if you create ions, you create current, the opportunity for it. So it sort of validates my point that a lot of electricity is about transferring a change in ionization between atoms, a change of their potential, their pressure.
And so it's no surprise then for you that the conductivity of seawater is 1,000,000 times higher. Think about it, 1,000,000 times higher than the conductivity of distilled water. And I would like to give you the number for water. So this is distilled water. That is about 2 times 10 to the 5th ohm meters. That is the resistivity. 2 times 10 to the 5 ohm meters.
About half as bad as
I have here a bucket of distilled water. I'll make a drawing for you on the blackboard there. So here is a bucket of distilled water, and in there is a copper plate, another copper plate, and here is a light bulb, and this will go straight to the outlet, stick it in, 110 volts. This light bulb has 800 ohm resistance when it is hot. You see the light bulb here. You can calculate what this resistance is between the two plates. That's easy. You have all the tools now. If you know the distance, it's about 20 centimeters. And you know the surface area of the plates, because remember the resistance inversely proportional with A. You have to take that into account. And you take the resistivity of water into account. It's a trivial calculation. You can calculate what the resistance is of this portion here. And I found that this resistance here is about 2 mega ohms. 2 million ohms. So when I plug this into the wall, the current that will flow is extremely low because it has to go through the 800 ohms and through the 2 mega ohms. So you won't see anything. The light bulb will not show any light. But now, if I put salt in here, if I really manage to put 3% in weight salt in here, then this 2 mega ohm will go down to 2 ohms. A million times less. So now, the light bulb will be happy like a clam at high tide because 2 ohms here plus the 800, the 2 is insignificant. And this is what I want to demonstrate to you now. The enormous
Yes, and also the interesting thing is you can do electrolysis this way, create hydrogen and oxygen. They'll both be mixed, from my experience. Collect them in a jar or something, and it really is a nice little pop it'll make. So, this is how you get hydrogen out of water. You have to plug it into the wall to use electricity.
Importance of increasing ions. I increased ions here by heating the air. Now I'm going to increase the ions by adding salt. So the first thing that I will do is I will stick this in here. There's a light bulb. And I make a daring prediction that you will see nothing. There we go. Nothing. Isn't that amazing? You didn't expect that, right? Physics works. You see nothing.
You didn't expect that, right? Physics works, you didn't see nothing. Of course, that's what we expected. The water's not a good conductor until you put salt in it. Got it. Yeah, play please.
If I take the plates out and touch them with each other, what will happen?
Spark.
There you go. But this water has such a huge resistance that the current is too low. Well, let's add some, not pepper, add some salt.
It's a very small light bulb, apparently 10 watts or something.
Yeah, the salt is there.
Didn't get any spark, but should have got a spark.
It's about as much as I would put in my eggs in the morning. Stir a little. Ah, hey, look at that. Isn't that amazing? When I bring them closer together, they become even brighter. Because L is now smaller, the distance is smaller. Bring them farther apart. It's amazing.
Can't really
Just
see that
a
much.
teeny little bit of salt, about as much as I use on my egg. Let alone, what the hell, let's put everything in there. Let alone when I put everything, then of course you go almost down to the 2 ohms, and the light bulb will be just burning normally. But even with that little bit of salt, you saw the huge difference. My body is a fairly good conductor. Yours too. We all came out of the sea, so we're almost all water. And therefore, when we do experiments with little charge, like the Van de Graaff, beating a student, then we have to insulate ourselves very carefully, putting glass plates under us or plastic stools to prevent that the charge runs down to the earth.
Yes, this is a problem.
In fact, the resistance, my resistance between my body and the earth is largely dictated by the soles of my shoe. Not by my body, not by my skin. But if you look at my soles, then you get something like this. And it has a certain thickness. And this, maybe 1 centimeter. This now is L in my calculation for the resistance, because current may flow in this direction. So that's L. Well, how large is my foot? Let's say it's 1 foot long, no pun implied. And let's say it's about 10 centimeters wide. So you can calculate what the surface area A is. You know what L is. And if you know now what the resistivity is for my sole, I can make a rough guess. I looked up the material and I found that the resistivity is about 10 to the 10th.
So it's pretty...
I can now calculate
pretty
What the-
high number. I mean, that's higher than water and lower than atmosphere, but it's pretty high.
Resistance is in this direction. And I found that resistance then, putting in the numbers, is about 10 billion ohm. So you will say, wow, oh, it's 4 actually. Well, big deal. 4 billion ohm. So you will say, that's an enormous resistance. Well, first of all, I'm walking on 2 feet, not on 1. So if I would be standing 1 the whole lecture, it would probably be 4 billion. But if I have 2 feet on the ground, it's really 2 billion. You will say, well, that's still extremely large. Well, it may look large, but it really isn't, because all the experiments that we're doing here in 26100, you're dealing with very small amounts of charge. Even if you take the Van de Graaff, say, has 200,000 volts. And let's assume that my resistance is 2 times 10 to the 9 ohms, 2 feet on the ground. So when I touch the Van de Graaff, the current that would flow, according to Ohm's law, would be 100 microamperes. That means in 1 second, I can take 100 microcoulomb of the Van de Graaff, but the Van de Graaff has only 10 microcoulomb on it. So the resistance of 4 billion or 2 billion ohms.
Pointing out that the resistance is, I don't know if there's a direct proportionality. Obviously, it doesn't mean much when the current is low, so it's not going to be a big deal. And it only becomes a bigger deal, percentage-wise, when you got higher voltages. I mean, you have higher currents. Something like that. So he's basically saying that because there's a low current, the voltage passes through the resistance of his souls, almost like the blue light effect, the draining effect, and that's enough to drain whatever little current he has to the ground. Something like that. So that makes you think about how to insulate things, because you have to insulate against the fact that the apparent resistance of some substances isn't enough if you've got very low currents. So low currents need more insulation, or you'll lose it all pretty quickly.
Ohms is way too low for these experiments that we have been doing in 26100, and that's why we use these plastic stools and we use these glass plates in order to make sure that the current is not draining off the charge that we need for the experiments. I want to demonstrate that to you, that indeed, even with my shoes on, that means even with my 2 billion ohm resistance to the ground, that it will be very difficult for me, for instance, to keep charge on an electroscope. I'm going to put charge on this electroscope by scuffing my feet. But since I have my shoes on, I'm not standing on a glass plate, the charge will flow through me. You can apply Ohm's law. And you will see that as I do this, I'm scuffing my feet now, that I can only keep that electroscope charged as long as I keep scuffing. But the moment that I stop scuffing, it's gone. Start scuffing again, that's fine. But the moment that I stop scuffing, it goes off again. Even though this resistance is something like 2 billion ohms. Let alone if...
So the point would be is that the scuff produces, but as soon as it's also at the very same time draining into ground. So he's creating a charge that goes up through his body, charges the electroscope, but the ground is also pulling it all back. So as soon as he stops for any amount of time, his net charge goes way down very fast, and that means he pulls the charge back off the electroscope. I think that's the correct interpretation.
I take my shoes off. I apologize for that. If now I scuff, he can't even get any charge on the electroscope, because now the resistance is so ridiculously low, I don't even have the 2 billion ohms, I can't even put any charge on.
It'd be nice if you put a piece of glass under it and then did it again. I always want something more.
The electroscope. It's always very difficult for us to do these experiments unless we insulate ourselves very well. And if somehow the weather is a little damp,
then the conductivity of many materials can increase.
that's why we always like to do these experiments in winter. so that the conductivity of the air is very low, no water anywhere.
Yeah, problem with that is in winter, you know, I'm using a gas stove to heat the house a little bit sometimes, and so that creates a bunch of humidity, and that's not good.
Here you see a slide of a robbery.
I have scuffed my feet across the rug, and I am armed with a static charge. Hand over all your money, or I'll touch your nose.
Oh, that's funny. But no sense of humor. No, I have none. Anyway, that seems to be it. I think the applause happens now or something.
This person either never took 802 or he is wearing very, very special shoes.
See you on Wednesday.
Ah, no applause. They didn't like it either. Yes, it was a little bit duller than the usual stuff, but okay. Take the good with the bad and such. So, that'll be it. So moving on. There's probably going to be a lot of this circuit stuff in a row for a while, and then we'll get on to something else, presumably, which might be more interesting. So, till then. And thanks for your attention.